Well, I can't make it any better, but guys, look, like this is their view. Like it's all sideways, like, and it's a document camera, so I can't like orient it, yeah, the other way. So if you're watching the video, I apologize. You're just getting a sideways and upside down view. Okay, so everyone, I want this review to be what's most helpful for you guys. What topics would you like us to go over? This is what we chose this morning, and it doesn't need to be the same as this, but where I've seen students struggle in the past is net ionic equations. Like this stoic is all or nothing. So either kids like got it or they struggled, okay? And redox reactions in acidic solutions. So those are the historical topics. What do you guys think? Do we want to add anything? Do we want to take anything away? That one works well. Yeah?
Yeah.
Okay. Let's do net ionic first. And the best way to study for any of our unit tests and the big final test at the end is the practice problems, like the ones that I print out for you guys that we come in and work on. So on the top it said 4.1 and 4.4, and then like halfway through it was where it changed to 4.2 and 4.3. So this is topic 4.1 and 4.4 practice problems. Like this is what it says on the top of the one that I'm going to look at. Okay. And then I want us to, we're like halfway through because we're going to jump to the 4.2 and 4.3. And then honestly, the one that we did that was really helpful is this one. Okay, let's look at 19, everyone. 19. So, a 20 milliliter sample of 0.5 molar HC2H3O2. Acid, how do I know? Hydrogen, exactly. Weak or a strong acid? Now what do we? It's weak. So you need to know your strong acid. The first one's lined up over here. So you see chlorine, bromine, and then iodine. So if you put hydrogen in front of those three, those are strong acids. Okay. So HCl, hydrochloric acid, HBr, hydrobromic acid, HI is like a hydroiodic acid. Those are strong. Then nitrate, NO3 with a minus, and hydrogen's a +1, and so then that's nitric acid. That's strong. Sulfate, SO4 2-. So I need 2 of these H pluses. That one's strong. And then the last one has chlorine, HCl, O4. Those are the 6 strong acids. Okay. If it's not on that list, then it's a weak acid.
Zinc only lasts about 2 periods. 2 and like a half. It worked for half of them, didn't work for half in 98 hours.
Okay.
So I poured it out and got rid of the ones that stopped working.
Okay.
So one of us has to set it up in the morning because I don't trust him enough because he'll be in there first hour.
I'm gonna be in, I talked to him, I'm gonna be in there first.
Okay.
Okay, no worries, I'll figure it out.
Okay.
Thank you.
But everything is ready to be poured in.
Yeah.
I just got rid of it so you wouldn't assume it worked.
Yeah, thank you. Okay, so, when it's a strong acid, then they separate. And if it's a strong base, then they separate. If it's a weak acid or a weak base, then they don't separate into the ions. Strong bases are a group 1 or a group 2 metal. Group 1 metal, group 2 metal, with hydroxide. We have a strong base, exactly. Weak acid, strong base. Okay, so now we mostly just need practice putting this together, pulling apart the ones that are gonna pull apart. So we're gonna take an acid, HC2H3O2, and it's gonna react with a base. Okay. And every single time an acid and a base react, it's a neutralization reaction, and we get water, liquid, and these ones were aqueous. Okay, here's where the water came from. An H plus for the acid and the OH minus from the base. Those come together for the water. Whatever's left over is the salt. So you get water and a salt. So we get sodium, and everyone, this is in group 1, so we know it's a +1, but if you forget, hydroxide is a -1, so it's a 1-to-1. Same thing here, if this hydrogen's a +1, then this whole thing has to be a -1, okay? So I'm gonna take sodium, and it's gonna be with C2H3O2, okay? When it's not an acid or a base, it's an ionic compound, a salt, a metal and a nonmetal, a metal and a bunch of nonmetals for a polyatomic ion. Then we have to check the solubility. And the solubility rules, they were like on page 26, something like that. No, it wasn't 26.
Yeah, it's not 26.
Because, yeah, that's the middle of our story time. Right after that.
It's on 38.
38, thank you. So on the top of page 38, solubility rules, all salts, that means ionic compounds, metals, nonmetals, all salts containing sodium, potassium, ammonium, NH4 plus or nitrate are soluble. So is this soluble aqueous, or should I have it be a precipitate solid?
It's soluble.
Okay. Now, on the test, the AP test and the unit test, when they are wanting you to do net ionic, they will say, what are the reacting species, or what species react? Because for a complete ionic, you get rid of the spectator ions. Those ones are not reacting. So whatever is left is the reacting species. That's the net ionic. So let's see. Oh, weak acid or base, don't pull it apart. So this one stays together. HC2H3O2, aqueous. Strong acids and bases we do pull apart. So Na plus aqueous, OH minus aqueous. Solids, liquids, and gases we don't pull apart. H2O liquid. Salts, metals, nonmetals, ionic compounds that are aqueous, we do pull apart. So we get Na plus aqueous and C2H3O2 minus aqueous. There's only one spectator ion. What is it?
Na.
Yeah, exactly. That's our only spectator ion. So if you get rid of the spectator ion, then you get the net ionic. Yep, answer is C. Okay. Yeah.
Why do you only split apart the strong acids and bases and not the weak ones? When they're aqueous?
Great question. It's the characteristic that makes them strong. So remember how we said something that's acidic has a lot of H plus in it, and something that's basic has a lot of OH minus. So when we put a strong base and it splits apart, that means we get a lot of OH minus. And so it's very basic, because that's what makes it a strong base. Where if we take a strong acid and any of these split apart, then we get a lot of H pluses, and that's what makes them strong. Weak acids and weak bases, they dissociate a little bit, meaning if I have 100 of these, 2 of them break apart. But it's not enough that we put it in an equation. Okay, more on that when we get to the acid and base unit. Okay, so what do you guys think? Do we want to do one more of these?
Yeah.
Okay, let's try, yeah, let's do the next one underneath it, 20. So this is it's one of the practice problem packets. So it says topic 4.1 and 4.4 practice problems. And then we're like well over halfway into it. And so like question 20, 19, 20. So now we're gonna do 20. Okay. A student places a piece of zinc solid into a beaker containing copper sulfate aqueous. After 45 minutes, the student observes a brown solid at the bottom of the beaker and that the solution has turned from blue to colorless. Okay, a couple things. When we write this one down, you'll see that it's a single replacement reaction, but when copper is in a solution, like when it's dissolved as an ion, it's blue, but when it's a solid, it's that like brown-red color, like pennies, okay? So if there's no more blue in there, there's no more aqueous copper in there. Okay, zinc solid reacts with copper sulfate aqueous. What is the zinc gonna kick out? Is it going to kick out the copper or the sulfate, and how do we know?
It's a 2 minus.
Yeah, like this is or a 2+.
2+.
Mm-hmm. And copper has to be a 2+ here because we know sulfate's a 2- and there's only one of those copper. A metal would kick out a metal, okay? Because we want a metal and a non-metal together. So that means we're gonna get zinc sulfate, and then we're going to get copper. Okay? So often, like you can assume this, that if one of the metals that was by itself was a solid, then the new metal that's by itself is probably a solid, and then this is aqueous. Like that's just a characteristic of a single replacement reaction, like when it's kicking that one out, okay? And then the prompt kind of tells us this, because it says that we went from blue, so copper as an aqueous, blue, to clear solution, so not copper as an aqueous, and there was a brown solid thing in there. Okay. Which of the following balanced equations best represents only species that react? So that's how they say net ionic. Okay. Solid, I don't break apart. Aqueous, where it's a metal and non-metals, I do break that apart. Aqueous, where it's a metal and a non-metal, I do break that apart.
What's going to be at the bottom?
Yeah, this is the clear solution. That's what's going to be at the bottom. Aqueous, and then solids, liquids, or gases, I don't break apart. There's nothing to break apart on this one. Don't forget this. The ion doesn't cancel with the non-ion. Only the ion cancels with the ion. Okay? So if that's the only one that cancels, zinc solid, copper 2+ turns into zinc 2+, copper solid. Okay. Questions?
Why do the solid ones not, why are they not ions when they're solid?
That's a good question. I wonder if it has to do with, like at that point they have a sea of electrons. So like metal as a solid, imagine each little desk clump as like a metal nucleus of an atom, and then the electrons kind of flow around it and go from one or the other. And so then it's not really being an ion because, oh, now it has the electrons, now it doesn't. Like they're just free flowing. Where these are like standalone ions, like that's a copper atom, that's a 2+ and it's floating in water. I think that's why. Yeah. Yes.
Why, like, like, what's the purpose in, right, in the net ionic form?
Yeah, great question.
What benefit?
All the titration that we did today started with a net ionic. And so there are some advantages. It can simplify math later when we get to acid-base stuff. And then, redox, where we were doing redox reactions in acidic solutions, that goes so much better when it's already in a net ionic. And that's the expectation, is I will give that to you in a net ionic before you even do the redox in an acidic solution. So that's a step we skip, but kind of answers your question of like, why is it important? Like, where does it help us? It makes it, with the balancing redox in an acidic solution, it makes it much easier. Yeah. Good question. Okay. Well, should we, if we have time, we can come back to it, but should we step over to either stoic or oxidation reductions in that acidic solution? What would you guys prefer? I think we'll have time to do both, but we might have a little bit less time for one. So do you want to spend more time on stoic or more time on oxidation reduction? Oxidation reduction? Okay, let's do that. Will you pull out the problem set 4.9 practice, topic 4.9 practice problems. It's the one that we just had like 6 of them, and the very last page had the answers on it. And then everyone, I looked at the test this morning, and the one that is most reminiscent of what you're gonna see is number 2. So I think if we could talk through number 2 together, then you'll do great on that part of the test. I'm sure you've probably already answered this one on number 2, so if you want to follow along, great. If you would rather like go to the very last page and just like write it down and do the steps again, awesome. But we're gonna just look at number 2. Okay. So here's what's going on. So first thing, we got to find the half reactions. And when we were doing the free response question today, I noticed students struggling with this, and it was just assigning oxidation numbers. So first thing I want to remind you, if something is a monatomic ion, this is a polyatomic ion. There's multiple types of atoms that make up this ion. This is a monatomic ion. It's one type of atom. Whatever the charge is, that's the oxidation number. Okay. There's nothing on this one, but if anything was in its pure elemental form, but not an ion, or like the copper solid we saw earlier, those are zeros. Okay, oxidation number of 0. Okay. You will see this on the test. I'm pretty sure it's on the multiple choice. Maybe the free response, but I'm pretty sure it was on the multiple choice. Oxygen, outside of like pure oxygen, we assign a -2 unless it's a per oxide. Something to oxygen 2, okay? In that scenario, oxygen gets a -1 instead of a -2. And so then we automatically know that whatever the other thing is, they have to be +1s for it to all balance out. So hydrogen peroxide, H2O2, that's -1, +1. There's sodium peroxide, all kinds of stuff. All right, so why is that? That's a great question. It's just a rule that they have with oxidation numbers, and there has to be a good reason, and I don't know it. Yeah. So this all 7 of these oxygens are -2. I'm gonna end up erasing what's down here, but I'm gonna start to help me, so. 1, 2, 3, 4, 5, 6, 7. Okay. The whole thing has to be a -2, and I have 2 chromiums. So what do they each need to be so that this whole thing is just -2? Let's try it. So if they were each +6, this 6 would cancel out there, that 6 would cancel out there, and then that would leave us with the -2. Okay. So each of the chromiums have an oxidation number of +6, oxygens -2. Okay? Now, again, oxygen is going to get a -2. Hydrogen, when it's with nonmetals, hydrogen with nonmetals is always +1. Okay. Hydrogen with metals are -1. So here's a bunch of nonmetals, so we get 6 of those. What do each of the carbons need to be so that the whole thing is neutral? If they were each a -2, then that would cancel there, that would cancel there, and that would cancel there, right? So carbons -2, hydrogens +1, oxygen -2. Okay, last one. Oxygen's a -2, each of the hydrogens are a +1, so it's different this time, but close. What do each carbon need to be this time?
-1.
If they were each -1, oop, as I write +1, then that would cancel there, that would cancel there, this one would cancel with those ones, yep, that's right. So -1, +1, -2. Okay. Again, free response or multiple choice, I can't remember, but I could ask you what oxidizes and what reduces. So chromium went from +6 to +3. Do you see how its oxidation number reduced? It went down, it became more negative. That is reduction. Okay. Also, Leo the lion says grr, right? So if I gain negative electrons, that would reduce my oxidation number. If I lose negative electrons, that would increase my oxidation number. I'd oxidize. So then oxygen didn't oxidize or reduce. -2 stayed a -2. Hydrogen +1 stayed +1. So what oxidized then? Carbon did. Its oxidation number became more positive. It went from -2 to a -1. Okay? So it oxidized. Okay. Not here, but on other questions, if chromium in Cr2O7 reduces, that makes it the what agent?
What was that?
If chromium in Cr2O7 reduces, it makes it the what agent? Do you remember?
It's weird.
It's, yeah, so it's just the opposite of what it did, okay?
What is
So,
the thing for acid and bases? What are the things called? Like, they have the exact same kind of, it's just the opposite.
oh, conjugate,
Conjugate.
that's what you're thinking, and it's the same pattern in that, like, if it's an acid, it turns into a conjugate base, right? Now, the one difference is that both of them are on the reactant side for oxidation reduction. So if this reduces, it is the oxidizing agent, okay? If this oxidizes, then it's the reducing agent, okay? All right. Now, we need to write the half reactions. So you take what reduced and everything that's with it, Cr2O7 2-, and we say it turned into Cr3. Oh, that didn't get much better. Then we'll take what oxidized and everything that's with it, C2H6O, and it turned into C2H4. Okay, half reaction. Okay, so essentially step one is figure out what oxidizes and reduces so you can write the half reactions. Okay? The next step is balance atoms that are not oxygen and not hydrogen. So we have 2 chromiums and only 1 chromium, so I'll put a coefficient of 2 there. 2 carbons, so I don't need to do anything on that one. Okay? So balance the atoms that are not oxygen or hydrogen. Okay. After we do that, we need to balance the oxygens with water molecules. So since I have 7 oxygens over here and nothing over there, I'm going to add 7 water molecules. So I'm balancing the oxygens with water molecules. Down below, I don't need to because it was 1 oxygen, 1 oxygen, so I don't need to add any waters to balance it. Okay. So again, the first thing we did was the half reactions. The second thing we did is we balanced the non-hydrogen and oxygen atoms. And then the third thing is we balanced oxygen with water molecules. Okay? Now we need to balance hydrogens with H+. So I have 14 hydrogens on this side, so I need to add 14 H+ on the other side. Okay, now you guys tell me, look at the bottom one. How many H+ and where do I put them?
2.
That's exactly it. Now, because it was 6 hydrogens, 4, 5, 6 hydrogens. Okay. Okay. We need to balance the charges with electrons. So everyone, I can only add negative electrons, and I don't need everything to be neutral, I just need it to be the same on both sides. And this is the part that usually trips up students.
And 2 electrons to the right.
On this one. And so 14, let me double check, because I'm not even, 14 plus 1 things, and 1 minus 2, and so then, so plus 12 over here, right? Okay, so close. So I have 14 items that are a plus 1, I have 1 item that's a minus 2, so that all together on this side I currently have a plus 12. On the product side, I have 2 items that are a plus 3 and 7 neutral things that aren't adding or taking away from the charge. So we got a plus 6. Okay. Always add the electrons to your more positive side because we're adding negative electrons. How many should I add? 6. Yeah, exactly. Okay. I don't need this to be 0 and that to be 0. I just need them to be the same. Okay. Beautiful. Now, the bottom one will happen to be 0, but it doesn't have to be. And so what I mean is right now there's 1 neutral thing, so this is 0, 1 neutral thing, and 2 plus 1 things. How many electrons, where do I put them?
2 on the outside.
So now this side is 0 and it equals that side that's 0. Okay, okay, we're almost done. I need the electrons to be the same. And so I have 6 electrons and I have 2 there. So I'm going to multiply this whole thing by 3. So this is going to be multiplied by 3, that's going to be multiplied by 3, that's going to be multiplied by 3, and that's going to be multiplied by 3.
And we're going to have to know all of these steps for the test, remember?
Yeah. And I really do just think it's practice. That they're not difficult, but it's like once I do it over and over, then I'm able to like remember. Okay, last step, cancel anything that shows up on both sides. And electrons should always cancel. So I have 6 electrons, 6 electrons.
These are my least favorite part of chemistry.
Well, these are fun.
They're
Like a puzzle.
My brain just never understood it.
Is that the slime lab?
No, this is
You're
different.
oh, AP.
I cleaned up the jewelry section as best I could, but you were correct.
Yeah, Billy left it destroyed.
Yeah.
Yeah.
I got rid of the little pieces,
Yeah. Okay, thank
and I
you.
tried to put everything else together.
Perfect. Okay.
I emailed you this time then.
Awesome. I haven't even looked at it yet.
Okay.
One other thing cancels. What cancels?
Hydrogen, 6 of them.
6 of them cancel. So 6 of these cancel. With 6 of those, how many are left over here? 8. Okay. Sometimes water cancels, so keep an eye out for that. It doesn't in this case. And then we just put them together now. So I write my reactants, I write my products. 8H plus, Cr2O, 7 2 minus, 3 O, and 2 7 water. H4O.
Gosh, wow.
Yeah, I know.
Boy.
If you have time, and that's that's such a critical statement for AP, right? If you have time, you can check your work by making sure that the atoms are balanced and the charges are balanced. If you don't have time, that's okay, move on. Like, that's the answer, okay? But I can check this by first checking on the atoms. 2 chromium, 2 chromium. The oxygens are a little hard, oh, sorry, the hydrogens are a little hard to track. 8 hydrogens plus 18, and so 26. So I got 26 hydrogens over here. I have 14 plus, oh, look, I dropped that coefficient. See, so that helped me catch my mistake. So I have 14 plus 12 more, so I have my 26. Okay. Oxygens end up being balanced. Let's do charges really quick though. 8 plus 1 things, 1 minus 2 things, 3 neutral. So 8 plus 1, 1 minus 2. So I got a plus 6 on this side. 7 neutral things, 3 neutral things, 2 plus 3 things. And so that's that.
When we do the numbers at the top of it,
Mhm.
does it figure out what reduces and what oxidizes?
That's all.
that?
Yeah. Yep. And that's a great question. That's something I saw when a few groups, when they're working on it, they were taking like those like trying to grab those charges. These aren't charges, these are oxidation numbers.
Okay.
Just to help us identify what is reducing, what's oxidizing.
Okay.
So if you have one like this where there's just 2 reactants and 2 products, if you just, because you can tell like when the chromium and the chromium, you just don't know which one's reducing. If you just do one of them and find out that's reducing, can you just assume the other one?
Yes. Yeah.
Oxidizing?
Absolutely. And so, this, where we were working through it more carefully, that's like your multiple choice where it's like, hey, what's oxidizing? And it says like chromium, because like the answers are like chromium because it goes from a plus 6 to a plus, you know, like, and so that case, but for this, 100%. Okay, any other questions on this side? Okay, it's 3:25 right now. You guys are good, I don't wanna keep you any longer than you want to be. So there will be 0 events, just like with those guys, like if you wanna get up, you wanna go, like you're good to go. Do you guys want to do any stoic though?
Can we do it for 3.9?
Yeah, that's like 3
Like
point.
today's lesson, that one was really.
Yeah, we can talk about 3.9, and then stoic, what do you guys, or what are you leaning towards? Stoic? Yeah, either way. Okay,
Whatever.
like, and I'm not joking, like, I'm feeling good, like, head out, like, don't feel like you have to stay, alright? All right, let's do, and do you have a preference, goalposts or BCCA table?
Goalposts.
Goalposts, okay.
BCCs are easy.
Okay, beautiful. All right, this is gonna be in our packet then, okay? So this is in our unit packet. Packet. Yep, of course, yeah. Hold on, let me exit. Let's try that again. Yeah, here it is. Okay. So, first thing, we're looking at tentatively like pages 23 through 30. But like look at page 24. So, if a problem just gives me one number to start off with, if it says, hey, you have this much of a reactant, and it doesn't tell you how much of the other one, or it even is nice and says like the other one is excess, okay? So if it tells you one of them, I find that the goalpost is the easiest way to go. Work is the fastest. You still can do a BCCA table on any of these. You could do a goalpost on any of them. But I've just found that the work tends to be longer when we use a BCCA table when they only give us one starting amount. Okay? So, what mass of P2O5, so this is grams of P2O5, right, is produced when we start with this many grams of just the phosphorus. Okay? I find that it really helps, especially students that are still kind of struggling with goalposts, make a roadmap. Like, no joke, we have a number. We know we are starting with grams of phosphorus. And I know that eventually I want to end with grams of P2O5. I know the only way to go from one thing, phosphorus, to something different, P2O5, is moles to moles, and I'm not currently in moles. So the first step is going to moles. Grams of phosphorus to moles of phosphorus. Once you're in moles of phosphorus, that's when it can transition. Moles to moles is when it's different items. So I'm going to go from just phosphorus to P2O5. Okay, I'm almost there. If the problem, and they do this a lot on AP tests, where they say how many moles of P2O5 can be produced from this many grams. If that said moles, then I would be done. I'd set up my goalpost. But it wants mass. So what's my last step? Grams of P2O5. Okay, so this goalpost is 1, 2, 3 transitions. These are the units that go on the top. Grams of phosphorus, moles of phosphorus, moles of P2O5, grams of P2O5. And then take those same units and put them diagonally down below. So this one will go down here, this one will go here, down here. Okay. Upper left is always what you're starting with. So we're starting with 172.1 grams of phosphorus. Anytime you have moles over grams or grams over moles, periodic table, right? So this is moles of phosphorus over grams of phosphorus. And so I would just grab the number for phosphorus. 30.9. 0.7, and that's grams in 1 mole, okay? Anytime you see moles over moles, that's the balanced equation. That's the coefficients in the balanced equation. So moles over moles. Phosphorus has a 4 in front of it. P2O5 has a 2 in front of it. You could leave it like that, or you could reduce it 1 to 2. You'll get the same answer either way. Okay? Back to grams over moles. So we're going to my periodic table. 2 phosphorus, 5 oxygen. So then I'm going to add all those up. Okay? 141.
41.94.
So let me make sure I get 141.94.
Yeah.
0.94.
Thank you. And it's always 1 mole. Like whenever it's grams over moles or moles over grams, it's 1 mole, and then the number goes with the grams. So this is the top of my fraction. That's the bottom of my fraction. So how I would plug this in is I would do parentheses. 172.1 times by 2 times by 141.94, close parentheses, divide, open parentheses, 30.97 times by 4, close parentheses. Okay. How many sig figs for our final answer?
3, 4.
Don't worry about this, just look at the beginning for goalposts. Whatever amount of sig figs you start with, that's what you end with, so we'll have 4 sig figs. So when we did this, what was our final answer?
394.4.
That's what we got, beautiful. Grams of P2O5. Okay. Okay, amazing humans, you tell me. We can do another one of these, we can do BCCA table, or we can be done. BCCA table, do one of those, and then Jevin, if you want, and anyone else that wants to, we can go over what we did today. Yeah, okay. All right, if you want to head out, you're good. Like if you're like, I got BCCA table, you're good, okay? So I'm going to do BCCA for anyone that would like to stay, and then I'll talk about today's stuff that was kind of hard for anyone else. Okay? See ya. Alrighty, BCCA table. I'm going to look at probably this one, number 7. Okay. So, number 7. It's page 27. First thing, I noticed that it's giving me 2 numbers. It's saying I have this much of this one, this much of that one. So that's the indicator to me that a BCCA table is going to go way easier than a goalpost. It didn't just give me one thing, it gave me multiple things. Okay? That means one's a limiting and one's an excess. And the important thing to remember is that only moles in a BCCA table. And these things are grams, not moles. Okay? Okay, so let me grab my okay. So I would take, anytime they give me this in grams, 24.5 grams sodium chloride, do 1-step goalposts to go to moles, okay? And then same thing here, where it was like 41.3 grams of fluorine gas. Oh, look down here, it's an F2, not just fluorine, and I do grams per mole. So that way, when I set up my BCCA table, I'm putting moles in there, okay? Now, we run that. So earlier when I did those ones, I got 0.419, etc. moles of this thing, and 1.08, etc. moles of the other. And this is a rounded number, but I'm not gonna use the rounded number when I calculate. Like when I'm doing calculations, I'm gonna go and grab the long number, okay? For products, before the reaction, it's always 0. We haven't made any of them yet, right? So for the products, before the reaction, we don't have any of those. Our reactants are gonna go away and we're gonna make our products, and that's what change occurs. So reactants are always a minus, products are always a plus. Because we're gonna lose reactants, we're gonna make products. The coefficient in the front tells me how much. So since this was a 2, it's gonna be minus 2x. Since that's a 1, it's minus x. And then plus 2x plus x. The next thing, write down what you started with, like 0.419, and then put the change after this, minus 2x. Because that's the change that's going to happen. We started here and we're going to minus 2x from it. 1.08 minus x, 0 plus 2x, 0. Okay. One of these reactants is the limiting, one's the excess, and we don't know which one is which yet. But whichever one is the limiting, it will equal 0. So I'm going to set them both equal to 0 to figure out which one it is. And this leads to our next C, which is calculate. We're going to calculate x for both of those. So I'm going to add 2x to the other side. So 0.419 will equal 2x. And then I'll divide by 2. And I got 0.2096, etc. equals x. This one's easy because I just moved it to the other side. 1.08 equals x. Okay. The smaller x is the true x value. Like this one is bigger, that's not x, and that means this does not equal 0. Bigger one, not x, that does not equal 0. Smaller one, that is x, and it does equal 0. Okay. The smaller x always has the one that equals 0, and that makes it the limiting. This one's the excess. Okay. And now that we know what x is, we can plug it in here, we can plug it in here, we can plug it in there. Okay. So I'm going to do 1.08 minus 0.2096. I'm going to do 2 times by 0.2096, and then just 0.2096. When I plug those in my calculator, I get 0.8772 and 0.4192, etc. Okay. Here's all the questions that you could be asked. Which one was the limiting reactant? Yeah, oh, and here.
Oh, sorry.
No, and you're right, we found it here, right? And so NaCl F2. NaCl, because that was the one with the true X value. So then what a question could be, what is the excess reactant? The other one, F2, right? Another question that they could ask you, how many moles of F2 was left over after the reaction? 0.8772. They could say, how many moles of NaF did we make? 0.419. They could say, how many moles of Cl2 did we make? 0.209. Or they could ask you grams of any of those things, and then you do a one-step goalpost. How many grams of F2 was left over after the reaction? Take this, one-step goalpost, moles to grams of F2. Okay. How many grams of NaF was made? Take this, one-step goalpost, moles to grams of NaF. Same thing with that, if they asked how much chlorine we made. Okay, questions? Yeah.
Would it be possible to do a goalpost and solve it that way?
Let me tell you how you do it. So you would do like those 4-step goalposts, right? Where we're going grams to moles to moles to grams, okay? And you would start with this number, and then you would go to one of the products, and then you would do it again for this number to one of the products, so you'd have to do that twice. And whichever one made less of the product is the accurate one. That would be the limiting, and that's how much of the product you actually made, not the bigger one. And if they wanted to know for the other products, again, you'd have to do a 4-step goalpost twice to figure out how much of it. Oh, unless you already knew your limiting from the earlier one, and let's say this is the limiting and that's the excess, which we found, then you could do grams to moles to grams of the new one, because you already know it's the limiting, and you wouldn't do it for the excess. So that's what I mean, where it's like, can you use goalposts? Yeah, but I think it takes longer, where if a BCCA table, it's still a lot, but I think it's quicker, where when they just give you one, the goalpost goes easier. Because then you just kind of ignore whatever the excess one, and you do it without that. So, okay. Other questions? Okay, awesome. All right, guys. Again, if you're feeling good, you're good to head out. I'm going to answer any questions that you guys have about the most recent stuff, what we did today, right? Like 4.6. And so if you are interested in that, feel free to stay, but don't feel any obligation to. Okay. I'm gonna pull up.
I think I'm more confused on like 45, because I understand like how.
Like page 45 in the packet, or what are we?
Yeah, page 45 in the packet, because like I understand where endpoints are, like I understand the whole like how it filters, like how they filter, how it like is introduced and mixed. And it's just kind of like once we get to the graphs and information, that's where I think that's
Okay. 3, 4, 5. Did you say 46? 45. Okay.
like 46 could totally be right.
Truthfully, I actually, and it was kind of in the middle of doing this problem while I was filming the notes for you. I was like, ooh, I don't love this question. That's what I kind of realized, like how, like as I was doing it. And the ones that we see that we did today in the packet are much better, reflection of the kinds of questions that you'll see.
Okay.
As far as this graph goes, and let me confirm this really quick. Free response. Okay, 4.6. Okay, so not there, and then also yeah. On this unit test, you're not going to see one of these graphs.
Okay, cool.
Okay? When we get to the acid and base unit, then we'll be doing them again. So it's more just kind of like setting you up for the acid and base unit. Okay?
Well, then I'm all good.
Okay, any other questions, guys? No? Okay, beautiful. Good work.
Thank you, Mrs. H.
Of course.
Mrs. H,
Mhm.
could you perhaps show like some questions that on 4.6 that could be on the test? Like similar problem types?
No joke, and I do this quite often. The or something on this. Yeah, right there. The practice problems that I give you, I would say 2/3 of your tests can be found in those problems. Like, not hiding, right? Like, right there. So, because we didn't have a ton of time for the multiple choice part today, like, I would study those. Those are the kinds of questions you could see on the test. Look. Yeah. And I have the answer key if you want to take pictures of it.